DNA Data Storage and Neuromorphic Computing, a comparison by Daniel McCleary.
And Liam Kirkpatrick.
Here I'm going to explain what DNA data storage is. It's essentially just a method of storing large amounts of data inside of molecules, such as like the human body's DNA. DNA of itself is incredibly dense and a stable storage medium that can store a vast amount of data for an extremely long period of time. The way that it works is it takes ones and zeros, converts it into a formula that it can be stored inside of a molecule, and then store it for however long you need. And then when they want to extract it, it's like the vice versa algorithm just to extract the data. Here's a little brief snippet on the side here that'll explain it.
Storing digital data in DNA. This is how the process works. First, the digital data is converted from zeros and ones to the four building blocks of DNA: A, C, G, and T. 00 becomes A, 01 becomes G, 10 becomes C, and 11 becomes T. Twist Bioscience then writes the sequence of DNA. DNA can be stored for thousands of years and is decoded when needed. Storing digital data.
So what is neuromorphic computing? Neuromorphic computing is a method of computer engineering where elements of a computer are modeled after the systems in the human body. So neuromorphic computing uses artificial neural networks to perform calculations and learn from that data. And it also, neuromorphic architectures also are often modeled after neurons and synapses. A synapse is basically, think of it like a bridge where neurons can connect and communicate with each other.
So I'm going to start by explaining the left-hand side of this spline. I'm going to leave it off to Liam to explain the right. So we'll start how DNA data storage is developed and operated. First of all, it's three major steps, which were briefly described in the prior slide. So the major steps we'll start is coding the data, synthesizing and storing this data, and then decoding the data. And then, as mentioned, coding the data is just binary code, ones and zeros, that holds information that is translated into DNA codes and codons using algorithms. The DNA molecules are synthesized using a chemical/biological process and stored in a container in a regulated environment, as in like cooling, just where the DNA molecules won't be damaged. And then once you want that information again, you take it out of the tube and then you decode it with the algorithms that they have came up with. So when the data is needed, the molecules are sequenced to reveal each individual A, C, G, and T in order, which brings them back to the ones and zeros that they were once before. Then I'll leave it off here for neuromorphic computing.
All right, so the steps in development and operation of neuromorphic computing is first you start with research and design. So researchers are going to study how exactly the brain processes information by studying the neural networks mechanisms that we have inside of our own bodies. Then you're going to construct the hardware and implement program and software. So after the design is complete, hardware will be constructed. Following that, programming and software are going to be applied to the hardware. And three, training the neural networks. So the neuromorphic computing system must be trained using a variety of different algorithms. Kind of almost works in the same way as an AI would, if you think about it like that. And then there's the application. Once the neuromorphic computer is trained, it can actually be used in day-to-day applications.
So here's like just a brief explanation and how these can kind of like collide with each other because they're both very similar, as in they use like concepts of the human body. Both are biological systems. DNA is inspired by the way genetic information is stored in cells, and then neuromorphic computing is inspired by the neurobiological networks of the human body itself.
And you can also combine them together to store and process information. So, for example, researchers at University of Washington developed a neuromorphic computing system that actually uses DNA molecules to store and process data.
Can be more efficient than traditional computing and storage methods. DNA stores a large amount of data in a small form for a long period of time, which makes it extremely reliable. And neuromorphic computing can potentially do very complex computational, expensive computing problems in real time and faster than your traditional computer. And if you can somehow like eventually combine them with like very strong components, like this could be like the next generation of computing.
And so this slide here, we just have two quick videos. The first one's going to go over neuromorphic computing, and the second one will be on DNA storage.
With neuromorphic chips, we're creating a huge parallel sea of neurons where each one operates without any prescribed order. My team came from a startup that Intel acquired applying research relating to asynchronous design. We have software developers, chip designers, architects, algorithms researchers that come from diverse backgrounds like physics and biology, even chemistry. Loihi is the world's most advanced neuromorphic chip. It has scalability built right into it, so we can chain together this neural fabric.
So that video there just quickly covers, and it shows off a neuromorphic computing chipset. And as that guy was talking there, he also explains that his team is filled with a bunch of different people like physicists, people that work in biology backgrounds. All sorts of different people come into play when you're creating these neuromorphic computing systems. And so we'll show this DNA data storage video now too.
So the only way we're going to make DNA data storage scale up to be usable and be, go mainstream is by automating it. And what we've done with the project that you're going to learn more about now is showing that it's possible to automate the entire process from bits to molecules and back to bits.
So that video is very brief, but it's just describing how it could be used in like a practical environment for like a day-to-day person. Because right now it's very hands-on, where if you want to store the data, it's very manual. It's a very largely manual process. So they're working on ways of making it automated for commercial use. And that is the end of our presentation. Thank you very much for joining us.
Yeah, thank you.